plan, we have 3 more class days, is we're going to cover the content for 12.1, 12.2, and 12.3. We'll wait and do everything else for chapter 12 until second semester. So when we get back in second semester, we'll do like a little brief review on chapter 12. We'll do a chapter 12 quiz. We'll do the in-class activity. We'll do the chapter 12 test. All that stuff will just be in second semester. I don't need to do it now. You guys don't need any more tests. It'll be fine. Okay? Sound okay to you guys? All right. So that's my plan here for the next 3 classes. We're just going to do a section a day, talk through what's going on, and then do the in-class activities. Your last problem set for the semester. What's up?
So when I reprinted it, it doesn't have the back on it, and I need like all of this. So can I just staple this over, or should I reprint?
Just put an X through the page you don't want me to look at,
Okay.
and then staple. It's fine. So the last problem set of the semester is going to be these chapter 12 homeworks. But that's it. That's the last grade to come in other than your IA. Whatever you have right now is, aside from the IA and this one more homework assignment, where if you've done all the homeworks, remember you get 2 drops. So, if you have 100% homework right now, you don't have to turn it in. It wouldn't make any difference. You know what I mean? Just reminding you. Many of you have 100% in homework. Or they're about close enough to it, right? All right. So let's kind of grind through this thing. So we're going to continue talking about probability like we did in chapter 8. We're just now going to talk about it in a different context. We're going to talk about something called a probability distribution. So what we're going to do is kind of create a function out of these probability calculations is kind of the idea here. Thank you. So this first section is about random variables. So we'll start by just defining what we mean by a random variable. That is a quantity whose value depends on chance. So for example, my random variable could be like the number of heads I get when I flip a coin 5 times. Yep, you can put it right here in the pile. Just there's blanks right up there. I got a pencil in the cup or whatever, you just staple it onto the front. It doesn't have to be like fancy or nothing. So like if it's the number of heads when we flip a coin 5 times, what are the possible values for that random variable? 0, 1, 2, 3, 4, and 5, right? If I flip a coin 5 times, the number of heads I could get would be 0 through 5, right? Okay. So there are 2 types of random variables. There's discrete random variables, where the variable can only take on a finite or even countable number of possible values. When we say countable in mathematics, what do we mean? It means that we could map that infinite set onto the counting numbers. So for example, like you can have an infinite number of values, but if the values are like just whole numbers, like if all the values are 2, 4, 6, 8, 10, etc., but it goes on forever, that's still countable. Thanks, Sam. Okay. The other type is a continuous random variable. That's a variable that can take on any value within some interval. So let's do some examples give you some random variables and talk about whether they're discrete or continuous. Sound good to you guys? Sure. All right. So the random variable B is the number of babies in a pregnancy. Is that going to be discrete or continuous? Discrete, right? How many babies could you have in a pregnancy? 0, 1, 2, 3, 4, 5, etc. But it's a whole number, right? There's no decimals, there's no fractions. Okay. How about M is the mass of chips in a packet? That is continuous, right? Could be like 10 grams or 10.1 grams or 10.01 grams or 10.001 grams or 10.00001 grams. Just as long as you have a scale accurate enough, you can keep measuring, even if all the chip bags are around 10 grams, you keep measuring, they can be continuous. Everybody feel okay there? T is the time taken for a runner to complete a 100-meter dash. Discrete or continuous? Continuous, right? They could take 10 seconds, 10.1, 10.01, 10.001. You get the idea, right? As long as you have a timer accurate enough, you can measure that and get as many decimals as you need to. And then the last one, random variable X, is the number of sixes obtained when a die is rolled 3 separate times. Discrete or continuous? Discrete, right? You can have only a whole number of times a 6 can come up. You can't get 3.5 sixes, right? That makes no sense. Just whole number of times. Does everybody feel okay about picking out whether things are discrete or continuous? Same kind of thing with measurement, right? If a measurement is going to be, or your data is going to be discrete or continuous. We talked about previously, same idea here. So when we talk about making a probability distribution, essentially a function for probability, one of the key things that we're going to have is how many different times or how many different ways an event can occur. So our first thing that we want for our probability distribution is a listing of every possible value for the random variable and the probability that each of these outcomes will occur. So just like in chapter 8, where we started with a sample space and a probability for each outcome, for probability distribution, we want the same thing. We need the set of all possible outcomes and then the probability attached to each outcome. So let's look at an example here and build a probability distribution for this. So here we say we roll 2 dice and want to find the sum of the resulting rolls. So our random variable would be the sum of the dice. Everybody's okay? What are the different values that random variable can take? Assume they're standard 6-sided dice. Not 1. 2 through 12. Everybody's okay with that? So the X is the values for my random variable. Everybody's okay with that? Then what I did is I listed the different ways that I can get that value for X by rolling the die. So I could roll a 1 and a 1. So there's just one way to roll a 2. For a 3, I could roll a 1 and a 2 or a 2 and a 1. There's 2 ways to roll a 3. And I kind of built that out for the rest of the values. Is everybody okay with that? So the sample point are like the individual outcomes for rolling 2 die. X is the value for the random variable, so that's the sum of the two die, and F is the number of ways that that value for the random variable can occur. So like rolling a 7 can occur 6 different ways, and those 6 ways I've listed here. Does everybody feel okay with my table? What is the number of ways going to matter for? Like the number of ways that I can get a 10. Why does that number matter? For my probability calculation later on, right? To calculate the probability of getting a 10, well, I find the probability of rolling just any 10, and I multiply it by 3, because it could happen 3 ways, right? Everybody's okay with that idea? Okay. So let's look at another example. Let's say we want to find the probability where we roll a die 3 separate times, and we're getting a 6, and then our random variable is going to be the number of 6s obtained when a die is rolled 3 separate times. Okay? So if I want the probability that X is equal to 0, that's the probability that after 3 rolls, we've gotten no 6s. Everybody's okay with that idea? That's what this notation is kind of saying. So if I said the probability that X is equal to 2, that would be after 3 rolls. That's the probability of getting 2 6s. So far, so good? So if I said the probability that X is equal to X, that is all the possible outcomes and their associated probabilities. That's essentially describing the probability distribution there. So let's build that probability distribution for X. So to do this, I'm going to build a tree diagram. So if I got to roll this die 3 times, how many branchings is my tree diagram going to have? 3. 1 for each separate roll. So here's 1 roll. I can get a 6 or not a 6. Since the die is a fair die, I know they're equally likely. So there's 1 in 6 chance of getting a 6 and 5 in 6 chance of getting not a 6. Then I'll have my second roll. So I have this branch. And then my third roll, so that branch. Does everybody feel okay with what I've drawn here? Okay. Now what I'll do is look at each of these terminations, the end of each branching here, and decide what that random variable value is and its probability. So this first one is 6, 6, and 6, so that's 3 6s. So the probability of getting that was 1/6 times 1/6 times 1/6. So there's that. The next one is 6, 6, not a 6. So that would have been 2 6s and calculated the probability. The next one would have been 6, not 6, 6. That's still 2 6s. And there's the associated probability. And I'm going to do this all the way down. Does everybody feel okay with how I'm doing the calculation here? Okay. So if I then summarize this all into one table, the probability that X is 0 is just 125 out of 216. There is only one way to get 0 6s. If I'm looking for the probability that X is equal to 1, the probability I've gotten 1 6, let's see though, there's 1, 2, 3 ways of doing that. So I'm going to take those and add them together. And then I chose to reduce the fraction. I probably wouldn't have done that in practice, so I would have just left the fraction unreduced. I'll explain why in a moment. And then we'll do this for 2 6s, again, there's 3 ways to do that, so I added them up. And then for 3 6s, there's only one way to do that. So my probability distribution would look like this. Is everybody okay with how I formulated this? Now, in practice, I probably would have, in my table, would have written the 25 over 72 as 75 over 216, and the 5 over 72 as 15 over 216. What would be the advantage of not reducing the fractions there? How much should these probabilities add up to? 1. Is it much easier to check that if they all have a common denominator? Yeah, that's probably why I would have done that. So like 125 plus 75 is 200, plus 15 is 215, plus 1 more is 216. 216 out of 216 is 1, so I'm pretty happy with what I see here. Everybody cool? Oftentimes, we'll represent our probability distribution with a histogram. So the histogram would look something like this. Remember, a histogram has no gaps between the bars in our bar graph. It's not a bar graph, it's a histogram. So these percentages here, where did I get these from? Yeah, just a fraction converted to a percentage, right? Yeah, that's all that is. Everybody feel okay about what I would have done to get this? Again, pretty easy. And then, as we observed earlier, that if I add up all the probabilities in my distribution, I better get 1. Okay, so far so good? So if you remember from chapter 8, we had these basic rules for probability. So for any event, the probability needs to be between 0 and 1. Could equal 0, could equal 1. The probability of the entire sample space needs to be 1. If the outcomes are equally likely, just the number of ways that that event can occur divided by the total number of events. The expected count or expected value, given that you've done something n times and each thing has probability A, should be n times A. And then the complement rule that P of not A is equal to 1 minus P of A. So what we're going to do is we're going to translate these now into the language of a probability distribution. Everybody's okay with that plan? So this becomes the probability that x is equal to x has to be between 0 and 1. The sum of all those probabilities has to equal 1. So the probability x is equal to x is just the total number of ways that x can equal x divided by the total possible outcomes. The expected count, or the expectation, is just the value of the random variable times the probability of that outcome. And then we add that up for each possible value for a random variable. And then the probability that x is not equal to x is equal to 1 minus the probability that x is equal to x. So again, same rules, we've just translated them into the language of a probability distribution with a random variable, but it's the same properties that are happening. Everybody feel okay? Hopefully none of that is surprising. What we'll do next is we're going to define something called a cumulative distribution function, which we'll abbreviate as a CDF. So the CDF is a total probability that some random variable x is at most the indicated value x. So an example of a CDF is this that's described before, where our random variable x is a student's scale score on their IA. So, for example, f of 2 represents the probability that students got 2 or less on their IA. So that it would be like the probability that or f of x is the probability that x is less than or equal to x. Everybody okay with that idea? Notice what's the last value for any cumulative distribution function? Better be 1. Okay. So remember back in chapter 5 where we looked at cumulative frequency graphs and cumulative relative frequency graphs? Same idea here. So, for example, the probability of a student scoring at most 4, so that'd be 4 or less, is 0.55, right? What if I wanted to know the probability of scoring like exactly a 7? How could I figure that out from this? Well, I could take the probability of 7 or less and subtract the probability of less than 7, which is exactly less than or equal to 6. The leftover should be exactly 7s, right? So 8%, just the difference of the two. What's the probability of getting exactly a 6? Yep, so 15. And continue to just kind of go down, right? So I'll just kind of scroll through this quickly. You guys feel okay? Just got to make sure we know the name. So this is my probability, or my CDF, my cumulative distribution function. This is my probability distribution. How do I know that this isn't real probability distribution? What do I have to check? There's 2 things I should check with this. Okay, so the sum of the probabilities have to be 1. And the second thing is, all of these probabilities should be between 0 and 1, right? They all have to be valid probabilities, right? I can't have this like this much of it add up to 1.5 and this one be negative 0.5 and look, it adds to 1 still. That makes no sense, right? They all have to be valid probabilities. So that's the first thing we check. They're all between 0 and 1. And the second thing is they all add up. When I add them all together, we get 1. Everybody feels okay there? Let's look at another example. So this says when people create codes for their cell phones, the first digit follows the probability model shown in the table below. So what is the probability you pick a first digit that is more than 5? What digits would we be considering? 6, 7, 8, 9. So if I call X the first digit of our cell phone passcode, so if I want P of X greater than 5, that's going to be P of X equals 6 plus P of X equals 7 plus 8 plus 9. So add those all up and I get 22.1%. Sure. So far, so good. What if I want a histogram for that probability distribution? What's a histogram look like? Bar graph with no spaces, right? So, bloop. No big deal, right? I mean, it takes a minute to draw it or whatever, but like, should be easy to draw, right? The x-axis is just your random variable possibilities, and your y-axis is just the probability. Okay. Next thing we're going to talk about is expectation or expected value. So the expected value or the mean value or average value of a random variable is what we should expect for the random variable over many trials of an experiment. So let's say we have the probability distribution given here. This should look familiar. This is our, where x is the number of sixes when we roll a die 3 times. So if I wanted to calculate the average number of sixes I roll, well, our formula for expectation is the value of the random variable times the probability of that the random variable takes that value, and we add that up for each possible value for the random variable. So this would be 0 times 125 over 216 plus 1 times 25 over 72 plus 2 times 5 over 72 plus 3 times 1 over 216. So I get 1/2. Does that make sense? So if on average, if I roll a die 3 times, I get the number of sixes I would expect to see is 1/2. Is it okay that that doesn't make sense in practice? Can you get 1/2 a 6? No, but it's okay. It's like saying the average family has 2.5 children. It's like nobody has 2.5 kids. Okay. Let's say the random variable x has the probability distribution shown below. We have 1 and its probability is 7c, 2 its probability is 5c, 3 its probability is 4c, 4 its probability is 3c, and 5 its probability is c. We're asked to find the value of c. How would I do that? The key here is we're told that it's a probability distribution. What do you know about probability distributions? The sum of the probabilities has to be 1. So I can say 7c plus 5c plus 4c plus 3c plus c is equal to 1. And I can just solve for c. Everybody feel good there? Okay. So if I know that c is 1/20th, and I want to find the probability that x is greater than or equal to 4, that's going to be 3 over 20 plus 1 over 20. Everybody feels good there? So if I want to find the expectation, how do I find expectation for a random variable? It's the random variable times its probability. And I do that for all possible outcomes for the random variable. So 1 times 7c plus 2 times 5c plus 3 times 4c plus 4 times 3c plus 5 times c. And then we'll plug 1 over 20 in for c. So 2.3 is my expected value, or my expectation, or my average value. Does that feel okay for everybody? Next thing, let's talk about how we calculate variance and standard deviation. So these are the definitions for variance and standard deviation that we were given previously. What we want to do is kind of adapt this so that we can use it in a probability distribution. So this was our definition for variance, our formula for variance, I should say. And this is our formula for standard deviation. Remind me in this formula, what is X bar? Mean. Great. So we're going to need that. So these are our formulas for mean, variance, and standard deviation. What I want to do now is I want to adapt these so that we have them described in the language of a probability distribution. So we've already done mean before. What's the same thing as mean? The expectation. That's the vocab that you want to use, which is just the value of the random variable times its probability, and we add that up for all possibilities. The variance is going to be the value of the random variable minus the expectation squared times the probability of that random variable for all values of the random variable. Is everybody okay with that? And the standard deviation is still just going to be the square root of the variance. Okay, let's look at some specific example and show you how we calculate variance and standard deviation in practice. So we'll return to this example. Remember, for this example, you already calculated the probability, or the expectation was 1/2. So I'm going to format this into a vertical. So the first thing I'm going to do is x minus mu. So that's going to be x minus the expectation. So 0 minus 1/2 is negative 1/2. 1 minus 1/2 is 1/2. 2 minus 1/2 is 3/2, so on and so forth. Everybody okay with how I got that column? Then we'll square it. Bloop. And then I'll multiply that squared value by its probability. So 1/4 times 125 over 216, 1/4 times 125 over 72, etc., etc. That's my next column. So far, so good. Then, because of the sum, we'll add those all up. Get 5/12, so that's our variance. To get our standard deviation, what do we do with that variance? Just square root it. So the square root of 5/12 is about 0.645. Feel okay? Not too bad, right? So here we're given or told a computer store sells a specific type of laptop. The number of laptops sold each day is shown in the table below. X is the potential number of laptops sold each day. So 0, 1, 2, 3, 4, 5 laptops. First thing it asks us to do is calculate the expected value of the demand. So how many laptops would we expect to sell on a given day? So to do that, I'll do 0 times 0.08, 1 times 0.4, 2 times 0.24, etc., and add those all up. I get 1.9. So the store should expect to sell about 1.9 laptops per day. Does that feel okay? Next, it says calculate the standard deviation. So just like before, I'm going to build out a table just like we did before. So I'll start by doing x minus the standard deviation. So there I get those values. Pretty cool with how I did that. Just x minus the expectation. So 0 minus 1.9, 1 minus 1.9, etc. Then we square those. Bloop. And we take these values and multiply it by the probability. And we add those up. And then to get the standard deviation, we just square root the variance. So far, so good. Okay. So what that would mean is, on a given day, the number of laptops sold on average will be 1.28 laptops away from the mean number of laptops sold, 1.90. So the number of laptops sold should be some number between 0.62 and 4.18, right? So between one standard deviation above and one standard deviation below. Now, for your reference, we don't really need to do this calculation by hand. Your graphing calculator can handle this quite nicely. If you'd like to follow along on your graphing calculator, I invite you to take it out and follow along. So I'm going to start by entering my data table, my probability distribution, into L1 and L2, as pictured on the screen. Okay. And then what I'm going to do is do the one variable stats. And I'm going to enter my list as L1 and my frequency list as L2. Make sure you're doing one variable stats. L1 is your random variable. L2 is the probability. And bloop. Notice the mean and expectation are both listed as 1.9. That's what we got before. The standard deviation is here. That's about the 1.28 that we observed earlier. So should you really bother doing this by hand? No, you don't need to. Feel good? Fran, you're making faces. You okay?
No, yeah. No,
okay.
Yeah.
Okay. All right. Let's say that we have this situation. One country published a study about its citizens. One question asked its households to report the number of persons living in the household. The table summarizes the data. And we're asked to convert that data into a probability model. So our random variable is going to represent what? We need to start by defining our random variable, which our random variable will be representing. Number of people in a household. Great. If I look at my table, what's the one place where we got a little bit of a problem? 7 or more. That needs to be a single value. So we're going to cheat a little bit. Guess what we're going to do to that? 7 or more. Just make it 7. So that's going to be my random value, or my random variable values. Does everybody feel okay there? Now we need to get a probability associated with each of these random variable outcomes. So if I look, the random variable 1 occurs 31.1 times out of 116, right? So the probability should just be 31.1 divided by 116. Bloop. I'll do that for all the possible outcomes. Everybody feel good on how I did that? Okay. So now I have a probability distribution, notice that I checked here to make sure it all summed up to 1. Always good to do that. Part B says, find the probability that a randomly chosen household has 4 or more persons. How would I do that? Yes. So I'd get about 23.7%. So far, so good? Yeah. Sure. Next thing we're asked is to find the expected value. So I'll start by writing down the formula for expectation. So that's going to be like 1 times 26.8, or I'm sorry, 0.268, 2 times 0.333, 3 times 0.162, et cetera, et cetera, et cetera. Add them all up. Or you could use your calculator. But our expected value is 2.512. Everybody's okay there? Okay. So again, or you could do the calculator. So far, so good. And then the last thing we're asked is to calculate the standard distribution. So again, could just use your calculator to do this. Look, it was right there on the previous screen that we already did. Ooh, that's pretty nice. All right, last example. What is the probability distribution of the discrete random variable x that counts the number of heads in 4 flips of a fair coin? What should I do to start this? Great. What's our random variable?
Like there's what you get from the coin.
Yeah, it's not heads or tails.
Well, you're just looking at heads.
It's the number of heads in 4 flips of a fair coin, right? It says basically right there. So what am I going to need next? I need the sample space in order to calculate the probabilities. To do that, I would build a tree diagram. How many branchings is my tree diagram going to have? 4, 1 for each coin flip. So 1 flip, 2 flip, 3 flip, 4 flip. Now I've written next to it, next to each of these terminations, what that termination represents. So it's the outcome head, 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 or head, 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 tail. I did that all the way down. Is everybody okay with that I've done that? When you have a situation with a branching like this, it's often quite helpful to do that. What's the probability of getting heads? It's just 1 coin flip. 1/2, right? What's the probability of getting tails? 1/2. So what's the probability for any path? Nope. Well, let's look. What's the probability for this one where we got 4 heads? It's 1/2 times 1/2 times 1/2 times 1/2, right? Okay, what about this next one that is 3 heads and a tail? It's 1/2 times 1/2 times 1/2 times 1/2. Also 1/16, right? Are they all going to be the same probability? Yes. So each of these have the probability, each of these outcomes have the probability of 0.0625. So, how many different ways can I get 0 heads? If I look down here, it's just one way, right? So it's just going to be that 0.0625. How many ways can I get 1 head? I see 4 of them. So it's going to be 4 times 0.0625. How many different ways can I get 2 heads? Ooh, 6. So 6 times 0.0625. 3 heads. There's 4 that there, so same idea. And 4 heads, just one way to do that, so another 0.0625. Everybody feel okay here? That's it for the notes. Let's do the in-class examples though, eh? Those are always fun. Yeah, I sure hope so. I'm just kidding. Of course you can. All right. In-class examples. So it says, suppose you have 2 fair dice, meaning all sides are equally likely to face up when it's rolled. The first die is 4-sided with the numbers 2, 4, 6, 8 on its faces. The second die is 3-sided with the numbers 1, 3, and 3 on its faces. Let X be the number that appears on the first die. Write a probability distribution for the variable X. What are the different outcomes for the random variable X? That's the first die. 2, 4, 6, 8. What's the probability of getting a 2? 1/4. How did you know that? Yeah, and it says that the dice are fair, right? That's key. If it doesn't say they're fair, you can't do this just like 1 and 4 kind of thing. So far, so good? Okay. Are all those probabilities between 0 and 1? Yes. Do they add to 1? Do I have a probability distribution then? Yes. Okay. So part B, it says Y is going to be the second die. What are the possible outcomes for Y? 1 and 3. What's the probability of getting a 1? 1 and 3. And the probability of getting a 3? 2/3. Great. Then we have let A be the total of the 2 die when rolled together. Write a probability distribution for the variable A. Okay. What are the different outcomes for A? I could get 2 and 1, so that would be 3. And then I could get 2 and 3, that would be a 5. I could do 4 and 1, that's 5, but I've already written it, so I'm just going to leave it. And then 4 and 7, or 4 and 3, that's 7. Actually, let's start writing down the probabilities along as the way we're doing this, right? So 2 and 1. Ugh, come on now. And then we had 2 and 3, and 4 and 1. Okay, 7 was 4 and 3, or 6 and 1. The next outcome is 9. That would be 6 and 3, or 8 and 1. And we have 11, which would just be 8 and 3. And that's it. Everybody okay with how I did that? And then part D says find the probability that A is greater than 5. Or so say greater than or equal to 5. So that would be 1/4 plus 1/4 plus 1/4 plus 1/6. Or you could have thought about that as the probability that x is less than 5. I should say 1 minus the probability that x is less than 5, which is 1 minus the probability that x is equal to 3. Get you the same thing. So you could do it by complement also. Either is fine. The random variable z has the following probability distribution. Find the value of k. The key here is that we're told we have a probability distribution. What can I do with that? Yeah, if I add the probabilities up, they better equal 1. So far, so good. So if I do that, what do I get? I get 8k squared plus 2k is equal to 1. So if I subtract the 1 over, I have that. What kind of equation is that? Start with a Q. Quadratic. Good. What are the different ways we can solve a quadratic equation? Factoring or the quadratic formula would be the big 2. Which one is Mr. Gulick going to prefer to do in this instance? Quadratic formula. Why am I going to avoid factoring here? The leading coefficient is not 1, which means that the factoring is usually kind of a hassle. You could do completing the square also, sure, if you're a masochist, that's okay. Keep in mind that the quadratic formula is just completing the square. Solving, it's just, we've done the solving already for it. All right, so what do I get? I get 4 minus negative 32, so that's 36. Square root of that is 6. So if I subtract the 6, and if I add the 6, so could k be 2 different values then? What do you think? What's my answer got to be here? Why not? But that's not the probability. That's k. But if I plugged it in, it would be k being negative means that one of the probabilities is going to be negative, correct? So can't be negative. So this one would be okay then. Because when I plug 1/4 in, are all my probabilities going to be between 0 and 1? They will be. Should be easy to see that by looking at thingamajiggers. Okay. Says the random variable q has the following probability distribution. And then it says, in addition, 4 times the probability q is less than or equal to 1 equals 5 times the probability q is equal to 3. Find the values for both A and B. So what can we say with this? I can say that, correct? Because it's a probability distribution. I can add the probabilities to get 1. Or really 6A plus 2B is equal to 1. So far, so good. Next, I'll use this piece. Oh, gosh dang it. This piece. So I have 4 times the probability that q is less than or equal to 1. So that could be q equals 0 or q equals 1 equals 5 times the probability that q is equal to 3. Or just 20A is equal to 10B. What can I say? What can I get from that? B is equal to 2A. What do you guys think? Yeah? If I substitute that in above then, I get that 10A is equal to 1, or just A is 1/10. And if A is 1/10, then B is 2/10. Feels okay? Just solved a little system there. All right, it says then in example 1, find the expectation for A. Yeah. So that's this using this. So that's going to be the value of the random variable times its probability. And I'll do that, add that up for all possibilities. Oops. I'm just going to So do I get 22/3? You trust me on that. Okay. Part B said let's do that for Z now. So that's this one. So that's going to be -3 times 1/4 plus -1 times 3 times 1/4 squared plus 5 times 1/4 plus 6 times 4 times 1/4 squared plus 10 times 1/4 squared. When I do that, I get 39 out of 16. You can trust me on that. Is everybody okay with how the work I'm doing to show this? And then the last one says to do the expectation for Q. It's going to be 0 times 4 times 1/10 plus 1 times 1/10 plus 2 times 1/10 plus 3 times 2 times 2/10. When I do that, I get 3 out of 2. So far, so good? Okay. Last question. You buy $10 worth of raffle tickets. You can place them in various drawings worth $20, $50, $200, $500, and $1,000. Let T be the random variable which represents the amount won on each ticket. T has the probability distribution given in the table below. Determine the probability that T is equal to 0. How am I going to find that value for the probability for T equals 0? Here's the hint.
Add the ones given and then do 1 minus that.
Feel good there? Who can tell me the expectation for T now? Do it on your calculator. Come on, it's a race. What a racing. Who's going to win?
It's 7.8.
Nope.
Oh god.
That's embarrassing.
Oh my god, that's not what it is. Put the second one in. Yep. For the frequency. Hold on. Whoa. So what was there? Wash over the house, that language.
Man, we're getting saucy today, huh? So everybody's all elated having their IAs turned in. They're like, yeah, I'm walking around. Mr. Kulik just told me I can get like a 50% and get a 5 on this class. Like, I'm hot stuff now.
Is it the mean?
42?
Would be the mean, yes.
No.
9.8 is correct.
That's the mean? That's what you said. No.
So the expectation and the mean are the same thing in a probability distribution.
Expectation in the mean.
They are the same thing in a probability distribution. So what is that saying then? What does 9.8 mean in context of this problem?
Yes, that's what I said. Let's go. Thanks, Carolyn. I appreciate it.
So we'd expect then to win $9.8 on our $10 worth of raffle tickets. So what's that mean then? How much should we expect to net? So lose 20 cents. Should we be playing in this raffle? No. We should not expect to be profiting from playing in this raffle. Not a good deal for us. The person running the raffle, good deal for them, but that's what you'd expect in a raffle, right? You wouldn't, people do raffles to make money. This, as far as raffle goes, this is a pretty good deal. If you're only winning, like losing 20 cents out of every $10 you invest, that's pretty fair raffle. Where is expected value going to be like extremely relevant? No, man. Well, I mean, yes, but I'm talking about like in like the real world. Gambling. So if you guys are doing any kind of, if you're doing any kind of sports betting and you're not thinking about thinking about your bets in terms of expected value, you're going to be losing money. You are what the casinos want you to do. Your worst bets, by and large, are going to be like compound bets, like parlays if you're in sports gambling.
Parlays are not.
Those are your worst kind of bets because the casino really does a poor job of giving you the proper odds on these compounding events. They do not fairly compensate you for how difficult these things are to get.
Instead, what should you bet?
Well, what you should be betting on are things where the casino has undervalued your bet, that your expected value should be positive. So what you'll see is that teams that are like public teams that have very large fan bases, the betting lines on those teams tend to be inflated because the goal for the casino is to try to get the equal amount of action on either side of their bets. So teams like the Lakers or the Cowboys that have big fan bases that tend to bet on the teams a lot, the betting lines on those teams are often inflated. So those are places where your expected value on the bet is probably better, than a team that doesn't have any fans.
So like the Jaguars?
Like the Jaguars, yeah. Now that's just like a real simple example, but the point spreads on like these public teams are often off in a way that it's the expected value for going against them is profitable. So
all parlays are bad. Stay away from them.
I would say in general they are bad. Yes, because you're not getting accurate value for your money placed. So the typical in a casino is on a one leg of a, like a regular straight up sports gambling bet, the casino's expected return is about 5%. On a parlay, their expected return is about 5% per leg. So if you have like a 3-leg parlay, they on average, instead of making 5% on your bets, they're making 15% on their bets. That's why they advertise the heck out of them and make it seem like this is such a great deal because they want you to throw your money away.
I was playing Fortnite the other day, and my friend was like making a parlay at the same time, and he was upset because he was losing.